Hello again, and welcome to the Sleepy Atom. Tonight we're going to gently drift into one of the most mysterious truths of the universe, one that affects every second of your life, and yet it barely makes a sound. Time. It ticks across your wristwatch, moves the clouds, brings us seasons, and slowly changes our faces in the mirror. But out there, in the quiet shadows of space, time doesn't always behave the way we think it should. It stretches, it bends, it slows to a crawl near gravity, and sometimes it seems to almost stop. And strangely enough, none of this is science fiction, it's real. So let's lie back, take a deep breath, and imagine what it would feel like to walk through a place where time itself changes shape, like soft clay in the cold vacuum of the cosmos. You don't need to understand every number. This isn't school. This is a soft journey, a kind of bedtime orbit around the strangest clock you've ever known. So tuck yourself in, and let's begin. What even is time? You've probably felt time move fast and slow during long lines, sweet moments, or sleepless nights. But if we peel back the surface, what exactly is time? Is it something flowing forward like a river? Or is that just how our minds choose to make sense of things? The ancient Greeks once said time was a god, always running ahead of us. Later, scientists treated time like a constant, like a perfect background beat the whole universe danced to. But that idea, the one you and I were taught in school, doesn't quite hold up under the stars. Out there in space, clocks don't tick the same way. Seconds stretch, minutes hesitate, hours can twist like ribbon. It's strange, but maybe not surprising, that we use so many metaphors to describe time. We call it fleeting, precious, heavy, golden. We say it flies, drags, heals, kills. That's because we don't just observe time, we feel it. Time is stitched into every heartbeat, every memory, every wrinkle and dream. But underneath all that, it's still just change, movement, one frame after another. If time is just change, then the way it passes must depend on how we're moving and what we're moving near. That's where Einstein came in with something quietly world-shifting. Time isn't fixed. It bends with gravity. It stretches with speed. And you are always carrying your own time. It may sound poetic, but it's also physics. The tick of your clock depends on your motion, your position, your mass, your surroundings. Time isn't one thing shared by all, it's a personal experience. A spaceship and a seaside cottage don't keep time the same way, even if they start with the same clock. And maybe that's the most mysterious part of all. You and I, we're not actually living in the same now, not precisely. Our present moments are quietly different, separated by gravity, speed, and space. We're each walking our own invisible timeline, gently curved by the universe itself. Time as a river. Imagine a river flowing gently past you, clear, steady, slow in some places, and fast in others. Now imagine that river isn't made of water, but of time itself. That's how many physicists describe what time feels like across the universe. Not a steady pulse, but a shifting current. The river speeds up when it flows past valleys of space and slows to a crawl near mountains of gravity. Just like water circles rocks, time flows around mass. Near a black hole, the current almost stops. Far out in deep space, the river runs faster again. It's all the same river, but it moves at different speeds depending on where you are. What's wild is, you're not just watching this river, you're inside it, floating with it. Every cell in your body rides that current. And sometimes, if you go fast enough or get close enough to something massive, you'll drift slower than the people you left behind. This is why astronauts who spend time in orbit age a little differently. They're moving faster and farther from Earth's gravity, so their time slips just a fraction compared to ours. It's not enough to notice in a day, but over years, it adds up. We're used to thinking time is like a metronome, click, 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 but in the real universe, that steady click bends and stretches. It curves gently like wind across fabric. And in those curves, we find some of the most beautiful paradoxes in physics. Why clocks tick slower in space. Let's say you take a clock, a real ticking clock, and send it up into orbit around the Earth. It's high above, speeding along in microgravity. You leave another identical clock right here on the ground. When you bring them back together, they won't agree. This isn't a mistake or malfunction. It's a built-in feature of our universe. The clock that went to space will be ahead. It will have ticked just a little faster than the one left behind. Why? Because gravity slows time. And in orbit, there's less of it. It's such a small shift, a few billionths of a second, but real enough that the GPS in your phone has to correct for it every day. Without accounting for time bending, your navigation would drift miles off course. The satellites know this, and they quietly adjust their ticking to match your earthbound pace. It's not just the distance from gravity, it's the movement too. Speed and gravity both shape time. That means the faster you go, and the lighter your surroundings, the quicker your time flows. It's like each clock has a personality, ticking slightly differently depending on where it's been. So when you gaze at the stars, you're not just looking into space, you're looking into many different versions of time. One for the moon, one for the ISS, one for you, sitting here now. The strange flexibility of now. Think about this. What does right now mean? You might say, well, it's this moment, the moment you're hearing these words. But what if I told you that someone floating near a black hole might not agree? Their now could include things in your future or your past. Time is flexible. What we call the present is just a slice, one angle of a much bigger shape called space-time. And that shape changes depending on how fast you're moving and what gravity you're near. For someone falling through deep space, now might stretch in a strange direction. It's like slicing a loaf of bread at different angles. Each slice looks different, but they're all part of the same loaf. That's how scientists see the universe. Your now is just one slice, and someone else's might be tilted slightly or stretched far back or ahead. This isn't science fiction. It's something GPS engineers, satellite scientists, and particle physicists all work with every day. Your sense of right now is an illusion, shaped by biology, motion, and mass. There's no universal clock chiming in the sky, and maybe that's okay. Maybe now doesn't need to be fixed. Maybe it's enough to know that every person, every star, every traveller in the dark has their own unique thread through time, softly unspooling like silk in space. You are a time traveller. It sounds wild at first, but technically, you're time travelling right now. Every second you live, you're moving forward in time. It just doesn't feel like a journey because you're inside it. But here's the part that bends the mind. The speed of your travel isn't fixed. It changes, slightly, subtly, and with the right tools, like rockets or black holes, it could be changed a lot. Time isn't just something that happens to you, it's something you move through. If you were to board a spacecraft and fly near the speed of light for a few years, then return to Earth, you'd find that decades had passed here. Friends older, the world changed, but to you, it only felt like a short trip. That's not fantasy. That's special relativity. We don't need warp drives to prove it. Every particle accelerator on Earth shows it. Particles moving near light speed live longer. Their internal clocks slow down. We've measured it, repeatedly. It's one of the most tested ideas in physics. So when you wake up tomorrow or drift to sleep tonight, remember this. You're not stuck in time. You're gliding through it, gently, quietly, a little faster or slower, depending on your height, your motion, and the unseen hand of gravity, the twin paradox. Picture two twins, identical in every way. They say goodbye at a space station, and one of them boards a spaceship traveling near the speed of light. The other stays behind on Earth. Years pass, slowly for one and more quickly for the other, and when the traveling twin returns, something strange has happened. She's younger, not metaphorically, actually younger. Her muscles, her brain, her blood, all aged more slowly while moving at high speed. Meanwhile, her earthbound twin aged normally. They shared the same birthday, but now their bodies tell two different stories. This isn't fiction. It's not just theory. It's a real prediction of Einstein's relativity, tested with atomic clocks and confirmed with fast-moving particles. Even our astronauts return with tiny differences in their time, proof that high-speed motion slows aging, even if just a fraction. The closer you travel to light speed, the stronger this effect becomes. And it's not just about time feeling slower, it is slower from the traveller's point of view. A second becomes a stretched ribbon, pulled gently across vast cosmic distances. So what does this mean for the future? Could we really leap into the far future simply by flying fast enough? Or is time still the one thing we never fully escape? Time feels different on mountaintops. Let's bring things back down to Earth for a moment. Literally, you don't need a spaceship to experience time bending. You just need a mountain. The higher you go above sea level, the farther you are from Earth's gravity. And that small shift? It speeds up your time, just a little. On tall peaks, your clock ticks slightly faster than it does at sea level. It's barely noticeable, but measurable. High-altitude atomic clocks gain time, tiny fragments of a second, just by sitting a few thousand feet above the ground. It might seem trivial, but it's real. If you live your entire life in a high-rise building, you technically age just a touch faster than your neighbours on the first floor. Their seconds are slower, tugged gently by Earth's stronger gravity below. And this quiet difference matters. It's part of why global navigation systems must constantly correct their clocks. GPS satellites orbit high above us, where gravity is weaker, so their time runs faster. If they didn't account for that, your map would lead you to the wrong street every single day. It's humbling, isn't it? Just a few kilometers up, and the rules of time already begin to shift. Makes you wonder what else changes when we step just a little closer to the stars. Aging at the space station. Every time an astronaut lifts off into orbit, they're not just leaving Earth behind, they're stepping into a slightly different rhythm of time. Up there, floating in microgravity aboard the International Space Station, time ticks just a little differently. At first you might think it should run faster. After all, there's less gravity. But the station is also moving at over 17,000 miles per hour. That speed slows things down. The net effect? Astronauts on the ISS age just a touch more slowly than those of us on Earth. In fact, after spending 6 months in orbit, an astronaut might return just a few milliseconds younger than expected. A tiny gift from time dilation. A blink, but a real one. It's not science fiction. It's physics, alive and humming silently in the background of every orbit. NASA has studied this. The famous twin study involved astronaut Scott Kelly and his earthbound brother, Mark. When Scott returned from space, researchers measured his body, brain, and cells, searching for subtle clues about how time, motion, and gravity shape our biology. So if you've ever dreamed of escaping time for just a little while, orbit might be the gentlest version we've found, a place where clocks float, and so do you. GPS satellites are just for time shift. Here's something easy to miss, but extraordinary once you see it. Every time you check your phone's location, when it finds your house or that quiet cafe on the corner, it's using a tiny miracle of time travel. The GPS system in your pocket only works because we've learned to bend time. The satellites above us orbit high and fast. That means they experience two time effects. Weaker gravity speeds their clocks up, and rapid motion slows them down. Together, these shifts create a difference of about 38 microseconds per day. That might not sound like much, but in GPS, even a few nanoseconds can throw off your position by kilometers. So engineers program each satellite to adjust its onboard clock, to sync perfectly with Earth's rhythm. A cosmic harmony of time, quietly managed so you can find the nearest pizza place. It's wild, isn't it? A bit of general relativity, discovered over a century ago, is now embedded in every smartphone. Invisible, essential, and deeply real. You carry space-time science in your pocket without even knowing it. So the next time your GPS reroutes you through a sleepy back road, remember, you're literally navigating through curved time. And it's all thanks to gravity, speed, and a few friendly equations. Your head ages faster than your feet. You don't need to leave Earth, climb a mountain, or orbit a planet to see time shift. You're doing it right now, just by standing up. That's right. The top of your head is aging slightly faster than your feet, by a few billionths of a second, every single day. It's because your head is farther from the center of the Earth. Even that tiny bit of extra height means it experiences slightly less gravitational pull, and thus time ticks a bit faster up there. Gravity gently stretches your seconds the higher you go. Scientists tested this using super precise atomic clocks. They placed one on a table and another on the floor. After a short while, the clocks disagreed. Just barely, but enough to measure. One experienced time faster, simply for being 30 centimeters higher. Now imagine this over a lifetime. If you spent your whole life laying down, your head and feet at the same level, you'd experience time just a touch more evenly. But standing, walking, stretching, every inch adds a whisper of difference. It's poetic, really. Your body is a timeline, a vertical one. Every part of you lives slightly out of sync. You're not just aging, you're aging in layers. Gravity slows time. Let's imagine something simple. You're standing at the bottom of a deep valley, and your friend is standing high above you on the hilltop. You both carry identical atomic clocks. You wave to each other, then check your clocks after a few hours. Quietly, they disagree. The clock at the bottom ticks slower. Gravity, even the soft, invisible kind, stretches time downward. The deeper into a gravity well you go, the more time hesitates. It's not broken, it's just gently resisting. And Earth's gravity isn't even that strong. Imagine standing near a neutron star, so dense that a single teaspoon of it would weigh billions of tons. There, time wouldn't just stretch. It would feel stuck, slow, syrup thick. Hours for you might pass like centuries outside. Einstein's general relativity first revealed this idea, that mass and gravity don't just pull on objects, they pull on time. They curve it, shape it, slow it, and we now have decades of proof. From satellites to signals, we can see the drag of gravity written into every clock. So if you ever feel like time moves slower when life gets heavy, you're not wrong. In the universe, heavy things really do hold time down. Black holes and infinite time. Now let's take that same idea and push it to its most extreme. A place where gravity isn't just strong, it's infinite. A black hole. A silent monster with no surface, no solid walls, just a boundary called the event horizon. Cross it, and time does something astonishing. From your perspective, falling in feels normal. Time flows. Your heart beats. You drift forward. But from outside, from anyone watching you fall, you never quite arrive. You stretch across time, slower and slower, until you seem frozen at the edge forever. This strange effect is one of the clearest ways we know that black holes distort time. Clocks near the event horizon slow down so dramatically they practically stop. Not metaphorically, but physically. 1 second there might take 1 billion years to match the outside. And if something could somehow hover near the event horizon, just barely outside, they could watch the universe speed ahead. Stars explode, galaxies move, civilizations rise and fall, all while their own seconds tick softly in place. It's haunting, isn't it? The idea that time, the one thing we think we understand, can melt into stillness at the edge of a black hole, where falling never looks like falling, and clocks forget how to move. Time near Jupiter. Black holes might be the drama queens of time bending, but even ordinary planets have a soft effect on time. Take Jupiter, the largest planet in our solar system. It's more than 300 times more massive than Earth. And that means its gravity nudges time ever so gently. If you stood on Jupiter's cloud tops with a high-precision clock, it would tick just a little bit slower than the same clock back on Earth. Not much, but measurable. And that slow tick is a clue that gravity, even without pulling you down, is tugging time itself. Scientists factor this into space missions, data syncing, and even radio signals. Time is delicate, and the deeper you sit in gravity, the more your seconds stretch. Jupiter's sheer size bends time across its own atmosphere, shaping how we study storms, moons, and magnetic fields. Even light changes pace when gravity is strong. Photons escaping Jupiter's grip lose energy, stretching into slightly longer wavelengths. It's called gravitational redshift. It's subtle, but it tells us that even light feels the weight of time here. So next time you see an image of Jupiter, remember, it's not just beautiful. It's a floating clock, slowing time ever so slightly under its swirling, silent weight. Light that escapes slower. Light moves at a constant speed. That's one of the few rules the universe doesn't seem to bend. But the way light behaves can still change, especially near gravity. When photons try to climb out of a gravity well, something quiet and strange happens. They lose energy, not by slowing down, but by stretching. A beam of light moving away from Earth gets redder. Its wavelength grows longer, not because it's tired, but because the space it's moving through is curved, and climbing takes effort, even for light. This is called gravitational redshift, and it's one of the earliest predictions Einstein made that was later proven true. Astronomers see it in the light from white dwarfs, neutron stars, and yes, the faint glow around black holes. The stronger the gravity, the redder the escaping light. Imagine that, colour itself, whispering about gravity, a soft cosmic code. You don't need a ruler or telescope, just look at the stretch of the spectrum and you'll know. Time slowed there. Light had to climb, and the climb left a mark. So even when light escapes, it tells a story about time, about weight, about the quiet struggles of a photon trying to leave a heavy place behind, the event horizon and frozen time. Let's return to the edge of a black hole, the event horizon, a place with no floor, no ceiling, just a boundary, a one-way door. From the inside, you fall through like it's nothing, but from the outside, time behaves like a frozen dream. If you could watch someone fall toward a black hole, a friend, a spacecraft, even a flashlight, you'd never see them disappear. Not really. Instead, they would appear to slow down. Their movement stretches, their light dims, their last image hangs in space. And this isn't imagination, it's physics. As the object gets closer to the event horizon, its clock, from your view, nearly stops. Its light gets stretched, fading into infrared, then radio, then silence. It's like watching someone freeze in time, just out of reach. But for the falling traveller, nothing feels strange. Time flows normally, no sudden stop, no warning. It's only outside observers who witness the strange stretch, the slow dance toward a line that never seems to be crossed. This paradox is one of the most poetic things about black holes. They're both there and not there, open and closed. And time, which once felt solid, becomes something you can barely point to at all. The deeper the shadow, the slower the clock. Let's imagine shadows, not the kind cast by trees or moonlight, but shadows of gravity, invisible zones where time itself becomes heavier, slower, stretched. The deeper into these shadows you go, the closer you lean into mass, the more time begins to hesitate. This isn't metaphor, it's measurable. A person at sea level ticks more slowly than someone on a mountain. An astronaut near a black hole ages slower than someone watching from afar. The deeper you step into the gravitational shadow, the thicker your seconds become. And strangely, it's not about movement. You could be perfectly still, not running, not orbiting, not doing anything at all. Just existing closer to gravity bends your experience of time. It's like the universe quietly pinches the seconds, gently squeezing them as you descend. Imagine time like syrup in a jar. Near Earth's surface, it flows easily, but near something massive, that syrup turns cold, thick, slow. It still flows, just barely. You're still breathing, still blinking. But from the outside, you might seem paused, softly held in place. And this means something profound. Time isn't fair. It's not equal everywhere. The shadows of space hold some moments longer than others, and in those shadows, clocks forget how to hurry. Time in a gravitational well. Let's paint a picture. Imagine space as a giant rubber sheet, flat in most places, but sagging deeply wherever something heavy sits, like a bowling ball resting on a mattress. That sag, that's a gravitational well, and inside that dip, time slows down. You can't see it with your eyes, but it's there, surrounding planets, stars, galaxies. The deeper the well, the more time bends. So when we say someone is in a deep gravity well, we're also saying their clock is ticking slower than ours. Even photons, particles of light, feel this dip. When light tries to escape from a gravitational well, it climbs slowly. It stretches, loses energy, and shifts colour. The deeper the well, the more dramatic the stretch. It's like trying to run through molasses. And for people, we don't feel the change directly, but precision clocks do, and equations confirm it. If you lived at the bottom of a deep well, away from sunlight, away from stars, your seconds would last longer, not in feeling, but in physics. This gentle effect is why astronomers use time to map mass, not just visible objects, but even dark matter. Because where gravity deepens, time softens, and in those softened seconds, secrets unfold. If you lived on a neutron star, now let's stretch the imagination a little farther. What if you lived on a neutron star, a place so dense, so heavy, so tightly packed that time would barely move at all? A single teaspoon of its matter weighs as much as a mountain. Gravity here isn't strong, it's unimaginable. If you could survive the surface, and that's a very big if, you'd find your clock ticking in extreme slow motion. 1 second for you could be hours, days, or even weeks for someone watching from far away. You would become a time traveler simply by being there. And what's strange is, you wouldn't feel different. Inside your body, time flows as it always has. Your thoughts, your heartbeat, your breath, they all move normally. But for the rest of the universe, you've become a quiet, gentle pause in the timeline. From above, your light would stretch red. Your image would distort, and you would seem forever caught in a slow-motion whisper, barely moving, barely aging, suspended by the weight of impossible gravity. Neutron stars remind us, time isn't fixed. It can be pressed like clay until it barely resembles itself. And if you stood there in the densest stillness, time might finally feel like silence. Could you ever watch the universe end? Let's imagine something wild. What if you could watch the entire history of the universe unfold in front of you? Stars being born, galaxies colliding, civilizations rising and fading, all in fast forward. Turns out, this isn't just fantasy. Under the right conditions, it's possible. If you hovered near a black hole's event horizon, not crossing it, just circling it closely, time outside would race ahead. For you, minutes would pass. But in the rest of the universe, millions of years could unfold. You wouldn't age quickly, but everything else would. It's called time dilation, stretched to its most dramatic form. Gravity near the event horizon slows your clock to a crawl, while the cosmos keeps spinning. If you stared outward, you'd see stars rushing through their lifespans, planets changing color, even galaxies shifting shape. And eventually, you'd witness the slow death of stars, the cooling of the universe, the fading of light, all in one lifetime, one long, quiet orbit near the edge. It's haunting, beautiful, and deeply real, at least in theory. Some physicists believe it could be done. So could you really watch the end of everything? Maybe not comfortably, maybe not safely. But in the shadows of space, time gives us windows no calendar ever could. Echoes of time in gravitational waves. In 2015, something astonishing happened. A ripple passed through Earth, not through oceans or air, but through space-time itself. It came from two black holes colliding 1 billion light-years away, and for just a fraction of a second, our clocks trembled. These ripples are called gravitational waves, gentle stretches and squeezes in the fabric of space and time. They carry the story of cosmic events across the universe. Not just what happened, but when. They are time's echo, a whisper from gravity itself. Gravitational waves don't make sound, but if you translate their frequencies, you can listen. And what do they sound like? A soft chirp, a rising note, the final heartbeat of a cosmic dance, black holes spiraling into each other and sending ripples out like rings in a quiet pond. These waves move at the speed of light, but they arrive late, because the events that created them happened billions of years ago. So every time we detect one, we're also reaching back in time, touching the past with a trembling hand. They remind us that the universe isn't still. It moves, collides, bends. And in that bending, time becomes music, a song we're only just beginning to hear. Light, the speed of causality. Let's begin gently with something that never changes. The speed of light. It's more than just a number. 299,792,458 meters per second. It's the speed limit of the universe. And more than that, it's the limit for cause and effect. Nothing can happen faster than light can carry the message. Imagine someone turning on a flashlight. That beam moves forward, but not instantly. It spreads across the room, then through space. The delay is tiny, but it's real. In the language of physics, light defines what is possible, what can reach what and when. This is called causality. If an event happens in one place and another happens somewhere else, light must have time to travel between them for one to influence the other. That delay, that space between events, that's time being respected. Even if we had the most advanced ship in existence, we still couldn't outrun light. Time wouldn't let us. Because light doesn't just illuminate, it sets the rules. If you try to break the speed of light, you don't just go fast, you risk undoing time itself. So when we say light is constant, we're also saying time is safe. Nothing can sneak ahead of it. Nothing can cheat. And that soft safety holds the cosmos together. When speed slows clocks, let's revisit that famous twin one more time. This time she's not near gravity, she's just moving, fast, really fast, near the speed of light. And as she moves, her time begins to stretch. Not because anything is broken, but because speed, all by itself, bends the tick of a clock. This is special relativity, and it tells us something quietly strange. When you move fast through space, you move slower through time. So if you fly away from Earth and then return, everyone else will have aged more than you have. And it doesn't take science fiction speeds to prove this. We've done it in labs. Fast-moving particles live longer than they should. Atomic clocks flown around the world show measurable differences compared to ones left behind. Even airplanes create tiny, trackable time delays. The faster you go, the more you borrow from time. It's like you're trading space travel for aging. You move through space, and time gives you a small discount, a quiet bonus tucked into each mile per second. So even though we feel still, the universe sees us in motion. And every motion, no matter how small, leaves a fingerprint on time. A little delay, a gentle pause, a softened second. Time dilation in everyday travel. You don't need to ride a rocket or orbit a black hole to experience time dilation. You've already done it, on a train, in a car, on a plane. Each time you move, even at modest speeds, you stretch time by just a fraction. It's tiny, but it's there. The faster you go, the more your personal time slows down compared to someone standing still. It's not noticeable in daily life, but our best clocks notice it. They record every nanosecond and they whisper back, "That drive made you younger by a billionth of a second." It's comforting in a strange way. You don't need a sci-fi adventure to be a time traveler. You just need motion. Every step, every jog, every commute shifts your clock ever so slightly away from perfect alignment with everyone else's. Of course, it's not enough to stop wrinkles. Not yet. But it reminds us, time isn't rigid. It's personal. It bends quietly around your life, your pace, your path. Every motion you make leaves a ripple in your seconds. So tomorrow morning, when you get in a cab or board a flight, remember, your watch might be ticking just a little differently. Your time is uniquely yours. The International Space Station's time lag. Let's return to the edge of Earth, where a spacecraft orbits every 90 minutes. The International Space Station, a floating home, moving at over 17,000 miles per hour. Every astronaut aboard lives in a slightly slower stream of time. Why? Because of two competing forces. First, they're farther from Earth's gravity, which would make time faster. But they're also moving very fast, which slows it down. The result is that motion wins, and their clocks tick a little slower than ours. Not by much, just a few milliseconds over 6 months. But it's enough to track, enough to measure, enough to prove that time isn't universal. Even two twins born together can quietly drift apart just by choosing different altitudes and velocities. NASA's real-life experiment with the Kelly twins showed this in action. Scott, who lived on the ISS, returned to Earth with subtle differences in his biology, some expected, some still mysterious, but time was the most elegant one of all. So next time you look up and spot that bright dot drifting across the night sky, know this: someone up there is aging slower than you, floating through a different rhythm of now. High-speed muons and proof of relativity. Let's meet a strange little particle called a muon, born high in Earth's atmosphere from cosmic rays crashing into atoms. Muons are unstable. They decay quickly. Their life is brief, almost too brief to reach the ground, but somehow they do. If you measure the distance between where muons are made and where they land, it shouldn't be possible. Their lifespan is too short. Their speed is fast, but not enough, unless their clock is slower than ours, and it is. As muons rush toward Earth at nearly the speed of light, time bends for them. Their decay slows. From our perspective, they live longer, not because they're stronger, but because their time is stretched. This is one of the most beautiful proofs of relativity, not a theory in a book, but a daily truth falling from the sky. We've measured it, detected it, and every muon that lands near your feet carries a quiet message. I lived long enough because time slowed down. Tiny travelers from space, stretched seconds, and one of Einstein's most elegant ideas written not in ink but in falling particles. Quiet proof, drifting through the atmosphere, one soft decay at a time. Photons don't experience time. Here's something quiet and almost too strange to believe. Light, the thing we see with, the stuff that warms our skin, doesn't feel time, not in any normal way. A photon moving at the speed of light is timeless. For it, the moment it is born and the moment it is absorbed happen in the same instant. Let that rest in your mind. From the photon's point of view, and that's a loose term since it has no eyes or clock, its entire journey happens all at once. There's no before or after, no waiting, no travel, just blink, and it exists across space. This doesn't mean photons are magic. It means time itself doesn't behave the way we think when you go fast enough. Light doesn't move through time. It simply is. A thread stretched from source to destination, skipping the in-between. A straight line through a dimension we can't fully touch. And when we say light takes 8 minutes to reach us from the sun, that's true. But only from our perspective. From the photon's view, there was no journey, no distance, no duration, just one infinite now. So the next time sunlight falls on your hand, try whispering to it, "Welcome," because what you're really touching is something that never experienced waiting. It just was. And now it's here. The observer's dilemma. Let's play with a thought experiment. 2 people, one on a train moving near light speed, one standing still on a platform. A flash of lightning hits both ends of the train at the same time. Who sees it first? The answer isn't simple, because time isn't simple. To the person on the platform, the flashes happen together, perfectly synced. But to the person on the train, rushing forward, one flash reaches them before the other. Same event, same universe. But time itself arranges differently for each person. This is the observer's dilemma, a core truth in special relativity. There is no universal now, no moment that everyone, everywhere agrees on. The faster you move, the more you drag your version of time with you, and suddenly, even simultaneity becomes slippery. This might sound unsettling, but it's also freeing. It means the universe allows for multiple realities, not in the fantasy sense, but in how events unfold, how cause and effect stretch and twist across motion. Time adapts to your story, your pace, your motion. So if someone ever tells you it happened exactly like this, maybe, but maybe not. In the shadows of space, time tells slightly different stories to every traveller. The twin paradox, revisited. Let's revisit the twins. One final time. One stays on Earth. The other travels far into space at near light speed, then turns around and returns. When they reunite, one is older, one is younger, and neither of them cheated. Time simply played favourites. This isn't a trick. It's not imaginary. It's been proven, tested, modelled in physics. The twin who travelled experienced time more slowly due to motion. The twin who stayed aged more. They were born together, but now they live slightly out of sync. And this isn't just about clocks. It's about biology. Heartbeats, memories, wrinkles. Time dilation doesn't just stretch seconds, it stretches experience. And in doing so, it creates a quiet kind of loneliness. Two lives, once shared, now lightly misaligned. We often think of time as absolute, but the twin paradox shows it isn't. Motion, gravity, direction, all can bend time's passage. And when you come back, the world might not have waited in the same way. This thought that travel changes time is both beautiful and bittersweet, because it means even our best journeys quietly cost us time with others, not in days missed, but in the rhythms of existence itself, time and the edge of the universe. Now let's float outward, as far as we can go, to the edges of the observable universe, 46 billion light-years in every direction, but not because the universe is that old, it's because space itself has been expanding while light travels through it. And here's something strange. The farther we look, the older the light becomes. We're not just seeing distance, we're seeing time. When we look at a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. It gets more poetic. Some galaxies are now too far for their light to ever reach us again, because space is stretching faster than light can bridge. Those galaxies still exist, but they've slipped over a cosmic horizon. We'll never see their now. So at the edge of everything we can detect, time doesn't stop. It vanishes. Not because it ends, but because our connection to it breaks. Beyond that limit, we can't say what's happening anymore. The light is gone, and with it, time's whisper. This is the softest kind of mystery, a silence not of sound, but of information. At the edges of space, the past still speaks, but the present has already moved beyond our reach. Why now isn't universal. And now we come to something that feels unsettling at first. There is no single now, no grand universal clock that ticks the same for everyone. In fact, your now and mine might not match at all, especially if we're moving or far apart. Time is personal. Relativity showed us that simultaneity depends on where you are, how fast you're going, and what's near you. Two events that are now for one person might be past or future for someone else. Not metaphorically, literally. This means every being in the cosmos experiences a slightly different version of time, not just in memory, but in physics. Their present moment, their now, ripples outward from their position and path like a soft pulse across space-time. It can be hard to accept. We want time to feel stable, shared, synchronized, but the deeper truth is gentler. Now is a moving thing, a thread stretched through your story, uniquely yours, brushing up against others, but never exactly the same. And maybe that's what makes time so intimate. It's not a stage we all stand on, it's the whisper we each carry through the dark, our own rhythm, in a universe full of drifting clocks. Was there time before time? Let's ask the quietest question in cosmology. Before time began, what was there? Can something exist without time? It feels like asking what's north of the North Pole, a question with no footing. Yet scientists have tried to answer it with gentle honesty. The universe began, or at least expanded into form, about 13.8 billion years ago. But that beginning includes time itself. So when we say, before the Big Bang, we're using words that don't quite fit, because time may not have existed at all. One idea is that the Big Bang wasn't the beginning, but a transition, a bounce from a previous universe collapsing. Another view says that time might emerge from deeper laws, like steam emerging from boiling water. In that case, time is a product, not a foundation. And others say the question itself is broken. If time didn't exist, there is no before, just a kind of timeless, formless state we can't picture. A silence deeper than physics. A pause not between events, but before event itself was possible. It's humbling. Maybe the mystery isn't something we solve, but something we stand in, quietly, like being in a cathedral with no walls. The birthplace of time might not have a clock at all. Entropy, time's one-way street. Why does time move forward? Why do we remember the past but not the future? The answer may come down to something called entropy, the tendency of things to become more disordered over time, from neat to messy, from structure to chaos, from young to old. A broken egg doesn't unbreak. Smoke doesn't gather back into wood. These aren't just accidents, they follow the arrow of entropy. The universe moves from low entropy to high, and with that, time flows forward like a slow river. This doesn't mean things fall apart quickly, it means they fall apart naturally. Left alone, any closed system drifts into disorder, and that drift is what gives time direction. It's not the ticking of a clock, it's the spreading of possibilities. And strangely, the early universe had very low entropy. It was ordered, simple, compact, and that initial neatness gave birth to the arrow of time, like winding a spring that slowly uncoils for billions of years. So when you see a shattered glass or a wrinkled page, know this. It's not just damage, it's time expressed through entropy, the quiet law behind every memory and every forgotten yesterday, time crystals and looped moments. Now let's dip into something newer, stranger. A recent discovery, time crystals. No, not from fantasy stories. Real measurable systems created in labs. These crystals don't break time, they loop it. They exist in repeating states without using energy, like a heartbeat that never tires. In normal crystals, like quartz or salt, atoms arrange in repeating patterns through space. But in time, crystals, the repetition is in time. The atoms change in a rhythm, over and over, like a skipping record that never wears out. This challenges a lot of assumptions. Most systems need energy to keep moving, but time crystals move through their phases without spending energy. It's like they dance through time without aging, forever suspended in a kind of perfect routine. Some physicists wonder if time crystals are hints of deeper truths, about how time might behave in quantum systems or in places where standard physics breaks down. Others think they might become keys to future computing or time-based technologies. But whatever their use, the poetry of their existence remains. A physical object, living in a loop, pulsing without decay. A reminder that time, in the right light, might shimmer like music instead of marching like a clock. Why time may not be fundamental. What if time isn't real? That's not a trick question. It's a serious proposal in modern physics. Some theories suggest time isn't a fundamental building block of reality. Instead, it might be a side effect, a useful illusion, a shadow cast by deeper laws. In quantum mechanics and string theory, time doesn't behave the way we expect. Particles pop in and out of existence without a timeline. Events happen in no clear order. And in some equations, time drops out entirely, like a note removed from a melody. One idea is that space and time both emerge from something even deeper, a network of relationships, a structure of information. In that view, time isn't something ticking away, but something that emerges when matter interacts. It's like how temperature isn't a particle, it's a summary of motion. Maybe time is like that too, a summary of change, not a thing itself. And if that's true, then time could disappear under the right conditions. That might sound scary, but maybe it's freeing. Time may not bind us as tightly as we think. Maybe we're more than its passengers. Maybe we're its authors. If time runs backwards somewhere. One last thought. What if somewhere in the cosmos, time runs backward? Not in fairy tales, but in physics. Could there be regions, bubbles, or mirror universes where entropy flows in reverse? Where cause follows effect, in reverse? Some cosmologists say, maybe. If the Big Bang created two universes, one expanding this way, one expanding that way, then in that mirror cosmos, time might flow opposite ours. From our view, they'd be shrinking. From theirs, we would be. And here's the wild part. To them, time feels normal. They eat breakfast, grow older, dream. It's only from our perspective that their direction looks reversed. To them, we're the ones doing everything backward. In this view, time's arrow isn't universal. It's local, like wind. You feel it blowing one way, but over the hill it might shift. Time too could swirl in opposite spirals across the cosmos. It's only a theory, but it invites a gentler imagination. That maybe what we call beginning and end are just two sides of the same page. And somewhere, in the distant folds of space, time might be remembering its future instead of forgetting its past. The heat death of time. Let's look far ahead, farther than galaxies and stars. There's a theory in physics that says the universe might not end with a bang, but with a long, cold fade. A final stillness called heat death, not because it's hot, but because there's nowhere left for heat to flow. In thermodynamics, when everything is the same temperature, nothing moves. No energy can transfer. No contrast means no change. And without change, time loses meaning. It becomes like a clock in a dream, ticking in silence, but with nothing happening. Over trillions upon trillions of years, stars will burn out, black holes will evaporate, matter may decay, and what's left is a thin soup of particles, evenly spread, quiet and timeless. A cosmic waiting room with no one to wait for. It's not violent, it's not even sad. It's more like a candle that slowly burns out until the wick is gone and the air is cold. If the universe reaches that point, time won't stop, but it will become irrelevant, like a metronome in an empty hall. And yet, some whisper that this might not be the end, just a reset, a pause before a new beginning. Because even silence on the scale of the cosmos might carry the seed of sound again. Black holes and time's disappearance. Let's fall gently into the most mysterious objects we know, black holes. These aren't just gravity wells, they are warpers of time. The closer you get to the event horizon, that invisible boundary, the slower your time flows compared to the rest of the universe. If you could hover just above the edge, you'd see the cosmos rush forward, galaxies spin, stars burn out, civilizations rise and fall. But to you, just a moment would pass. Time would stretch like taffy, slowed into syrup, almost stopped. From the outside, someone watching you fall in would never see you cross the boundary. You'd appear frozen, suspended forever at the edge. That's not illusion. That's relativity. Time bent so far it loses its grip on cause and effect. And what happens inside a black hole? That's the deepest unknown. Some believe time ceases completely. Others think time turns into space, and space into time, a cosmic flip. A place where clocks can't tick because there's no future left to tick into. So black holes aren't just mysterious because of their gravity, but because of what they do to time. They don't just swallow matter, they digest the very rhythm of existence. White holes, a time-reversed mystery. If black holes pull things in, what pushes things out? That's the idea behind white holes, a hypothetical cousin of black holes, but in reverse. Instead of pulling everything in, a white hole spits everything out. Energy, light, matter, even time thrown outward like sparks. White holes haven't been observed. They remain theoretical, but the math suggests they might exist, or at least they might have existed during the early universe. Some even think the Big Bang itself could be a white hole's explosion from another realm. If that's true, then we live on the receiving end of a time-reversed funnel, a place where matter poured out from something else's collapse. In that story, black holes and white holes are connected, like doors on opposite ends of time's hallway. From our side, time flows forward, but from inside a white hole, it might run in reverse, not metaphorically, but in entropy, in direction, in meaning. A universe made of outflow rather than collapse. Even if we never see one, the idea alone stretches our thinking. It asks, what happens if you flip time's arrow? What grows when time doesn't pull, but pushes? Is time a loop or a line? We often picture time as a straight road, yesterday behind us, tomorrow ahead. But some thinkers, ancient and modern, have asked, what if time is a circle, not a line, but a loop, something that returns to itself after enough revolutions? In physics, this is called a closed time-like curve, a theoretical path through space-time that bends so far it reconnects. If such paths exist, then a particle, or a person, could travel along it and eventually return to their own past. It sounds like science fiction, but some solutions to Einstein's equations allow it, especially near extreme gravity. Wormholes, spinning black holes, even the structure of space-time itself, might allow time to bend into a loop. But would memory survive the cycle? Would events repeat exactly, or only echo? Some theories say each loop might vary slightly, like a song played again with different notes. Others imagine an eternal return, a cosmos replaying itself forever. Whether time is a road or a ring, we're still walking it, and the shape it takes may not be obvious from the middle. Only when we reach the curve's edge might we realize we've been circling all along. The human brain's clock. Now let's bring it all home to you. You're not just a passenger in time, you're also a maker of it, because your brain doesn't just ride time's current, it builds its own rhythm. Your perception of time is personal, constructed moment by moment in pulses of thought. The brain has no single timekeeper. Instead, it uses multiple systems, visual cues, memory gaps, emotional spikes to estimate how long things take. That's why time seems to fly during joy and crawl during pain. Emotion bends your seconds. In fact, your brain is slightly behind reality. It takes around 80 milliseconds to assemble what you think is now. So even as you read this, your mind is stitching together a moment that already passed. And during trauma or deep focus, your brain alters time dramatically. Seconds can stretch. Hours can vanish. In these moments, we glimpse how flexible the brain's time truly is. Not a steady drumbeat, but a trembling string. So while physics defines time mathematically, your experience of time is something else. It's woven from memory, mood, and meaning. Time is something you feel, and that feeling, That's the heartbeat of your own private universe. Can time ever be controlled? Let's entertain a wish as old as memory. Can time be controlled, slowed down, paused, or even rewound? In science fiction, the answer is easy: a button, a spell, a machine. But in physics, it's more subtle. Time can be bent, but not broken. We already know that velocity and gravity can stretch time. Astronauts orbiting Earth experience milliseconds less than us. In theory, near a massive object, like a neutron star, you could stretch a lifetime into a blink. But it's not under our command. Not yet. Some researchers imagine future technologies, exotic matter, negative energy, quantum computing, that might one day allow us to bend time more dramatically, create bubbles where time moves slower, or find a way to isolate moments like snow globes. But so far, time remains stubborn. It flows forward, obeying entropy. You can't pause it. You can't undo it. What you can do is savor it. And maybe by paying attention, we slow it just enough to remember what mattered. So while we may never hold time in our hands, we can still shape how it feels. And in that soft influence, perhaps we've already begun to touch the edges of control, dreams and the timeless mind. Now close your eyes for a moment and imagine a dream. How long did it last? 10 minutes? An hour? A second? Time in dreams is not time at all. It stretches and skips. It folds events into flashes and memories into feelings. In dreams, clocks lose their meaning. The brain in REM sleep behaves differently. It generates sequences not by logic, but by association. Scenes change without warning, and your sense of time becomes emotional, not measured. That's why dreams often feel longer or stranger than they actually are. Some researchers believe this is because the brain's normal time tracking system powers down during sleep. Without it, we float. Our inner clock loses anchor. Events don't need order, and so the dream becomes a timeless theatre. But even more curiously, some near-death experiences, deep meditative states, and lucid dreams report a kind of eternal moment, a timeless clarity, not a blur, but a crystal, as if time had paused, not with stillness, but with fullness. Perhaps in the mind's deepest spaces, time isn't needed. Or maybe time is something we wake up into, and sleep is a gentle return to what we were before the clock began. Animals and time perception. Let's move softly into the animal kingdom. Do animals perceive time like we do? A fly reacts faster than a human. A tortoise seems unbothered by urgency. But under the surface, their brains are keeping time too, just on different tempos. Researchers found that smaller animals with faster metabolisms often perceive time in more detail. A fly sees your hand approach in slow motion. A hummingbird navigates through air like a ballet in bullet time. Their lives may be shorter, but richer in micro moments. Larger animals, elephants, whales, may experience time more slowly. Their hearts beat less often. Their changes come in seasons, not seconds. But that doesn't mean they're unaware. Their rhythms are simply longer, more drawn out, like a cello compared to a violin. Even your dog senses time, not with clocks, but with memory patterns, hormonal cycles, and the rhythm of your return. When you leave, time stretches. When you come back, it collapses into joy. So maybe time isn't species specific. Maybe it's like music. Each creature hears it in their own key, some fast, some slow, but all alive, all tuned to the symphony of change, timelessness in deep meditation. Now let's sit down, quietly, in the stillness of thought. In deep meditation, time begins to dissolve. At first, the mind notices minutes, breath, pulse, but slowly, those markers blur, and soon the meditator enters what some describe as timeless presence. Brain scans show reduced activity in regions linked to time perception during deep meditation, especially the parietal lobes. The sense of past and future fades. What remains is now. Not the clock's now, but a living, glowing now. Monks, mystics, and even ordinary people practicing silence often describe the same thing. Time disappears, not with chaos, but with peace. Not a blankness, but a fullness. Like the present moment stretches and fills the entire sky. This isn't just poetic. Neuroscience suggests that our concept of time is constructed by constant brain activity. And when that activity settles, time softens. Awareness becomes the only rhythm. And in that rhythm, something eternal whispers. So next time you sit in silence, notice how minutes feel longer, or shorter, or neither. That's not boredom. That's your brain stepping gently out of time's hallway and into its garden. Children and the elastic clock. Let's return to where time first begins for each of us. Childhood. Do you remember how endless summers felt? Or how waiting for a birthday seemed like forever? That wasn't just memory. As children, we actually feel time differently. A big part of it is proportion. A year to a 5-year-old is 20% of their entire life. To an adult, it's less than 2%. That's why days felt vast back then. Each one was a mountain of newness. Children also experience time more slowly because everything is fresh. First time riding a bike, first snowfall, first heartbreak. The brain records novelty in more detail, and more detail makes moments stretch. As we age, routine compresses time. Familiarity breeds forgetfulness. Weeks blur, years rush. But watch a child playing, and you'll see time unfold again, like petals, because they are still building their map of time, one wonder at a time. So maybe the secret isn't just to slow down, but to notice again, to see the sky like a child, to count the seconds not with a watch, but with a wide open heart. What if we lived forever? Let's stretch the human life into eternity. If you could live forever, would time change, or would you? Immortality is a fascinating lens, not just on biology, but on how we experience hours, days, decades. And scientists have quietly wondered, would forever make time less precious or more surreal? Over long spans, memory fades, novelty thins, experiences repeat. The brain may struggle to hold meaning if moments don't end. You'd eventually forget what young feels like, and maybe even what new means. Time might become background noise, like a fan humming in the next room. But something strange happens with long life. Moments don't just accumulate, they flatten. Without mortality, there's no deadline, no ticking. Urgency fades, and with it, the emotional intensity of time. You might feel weightless, untethered to change. Some researchers say our sense of time comes because we die. The awareness that moments end is what gives them colour. Without that limit, time becomes a hallway with no doors. Just walking endlessly without knowing what you're walking toward. So if we lived forever, would we still feel time? Or would we become beings of the present only, lost in a sea of stillness, searching for waves that used to crash but now only ripple? The multiverse and infinite time. Now widen your gaze. If our universe is just one of many, what happens to time in a multiverse? Some theories suggest that each universe could have its own time, its own pace, its own arrow, and that opens a strange door. What if in one universe time flows faster, 1,000,000 years per blink? What if in another time curls back on itself, or stutters like a skipping record? In some string theory models, these aren't just fantasies, they're mathematical possibilities. This means now might be meaningless across multiverses. You could have a twin version of you, somewhere, born 10 billion years before you and still alive, or already long gone before your first breath. Time in this case is local, like weather. It also raises wild spiritual questions. If consciousness can exist in one universe, can it echo in others? Can timelines overlap? Can choices ripple between them? Some physicists say no. Others aren't so sure. Because when it comes to infinite timelines, even the smallest event might echo forever. So when you look up tonight and feel that tug in your chest, that quiet suspicion that you're more than this single thread, maybe you're right. Maybe, somewhere in the tapestry, another you is wondering the same thing. Dimensions beyond time. Now breathe deeper. Some scientists believe time isn't the final edge, but just another face of something deeper, higher dimensions. In string theory and M theory, there may be 10 or even 11 dimensions. Time is just one, not above, not beneath, just one sliver. If true, then time might not flow at all. It might be static, like a landscape. We walk through it slice by slice, like flipping through frames of film. But all the frames already exist. Past, future, now, side by side, like rooms in a house. Some thinkers believe consciousness walks that hallway, not blindly, but guided, that the soul, or the observer, chooses which frames to experience. In that view, time isn't a master, it's a map. And awareness is what moves. There are whispers, too, of timeless dimensions, where cause and effect collapse, where everything exists at once, not in sequence. This isn't chaos, it's beyond understanding, not confusion, but completeness. Like seeing a movie all at once instead of second by second. It's hard to imagine, but maybe that's the point. Time may not be ultimate, it might just be our first language, and one day we may outgrow it. Does time have a shape? Let's return to a question we rarely ask aloud. What shape is time? We talk about it as a line, or a loop. But what if time, like space, has curvature, bends, folds? In Einstein's theory of relativity, time isn't separate from space. It's part of space-time, and space-time bends. This means that time near massive objects slows, not metaphorically, but measurably. The closer you get to a black hole, the more time curves. A second becomes a century. From a distance, it looks like a freeze. But from inside, it feels normal. Now imagine more extreme curvatures, wormholes, folded regions of space-time, bridges between moments. Not science fiction, but real possibilities. In these shapes, time could bend back on itself, or split, or allow shortcuts between now and then. Even on Earth, satellites account for time warping due to gravity. GPS would fail without corrections for these curves. Our clocks already obey the shape of time, quietly, constantly. So maybe time is less like a road and more like a ribbon. It can twist, curl, overlap, and somewhere in that graceful bend is you, floating, gently, between edges that no clock can fully measure. Could consciousness exist outside time? Let's end this section with a mystery that science still can't solve. Where is consciousness? Is it in the brain or something deeper? And here's the wilder question. Can consciousness exist without time? In some reports from near-death experiences or deep meditation, people describe timeless awareness, full, complete, but without sequence. They don't feel seconds. They feel being. It's not a blur. It's a clarity. Some quantum theories suggest that consciousness may not be produced by time, but merely filtered through it, like sunlight through glass. And if that's true, maybe consciousness is timeless. and what we feel as now is just a drip from a much larger ocean. Even in physics, time is fuzzy at the quantum level, and in certain interpretations, consciousness plays a role in shaping reality itself. Observation collapses probability, meaning gives form to moments. Could it be that time waits for awareness to arrive? It's hard to test, but the feeling remains. Sometimes when you sit very still, there's a presence that isn't counting minutes. It doesn't rush. It doesn't decay. It simply is. And maybe that's the truest part of you.